we had started talking about yield on Wednesday. And I know you already have in your vocabulary notes the definition, but here's a definition that kind of asks it as a question. When we are looking at the theoretical yield, what we want to know is, given the amounts of the reactants, what amount of product is produced? And usually when we say amount, we mean mass of the product that is produced. So if it just says what's the theoretical yield, assume it's looking for mass. So that's as far as we really talked on Wednesday. When you are in the lab, you may have an actual yield that is different. So you can probably figure out the actual yield is what you actually get. And it's usually less. So it is the amount of the product that is collected when the reaction is actually done. Now we say it is what is collected, not what is produced, because in any practical situation, the only thing that's useful to you is what you can collect. And so the reason that it is less is that some things can happen where you lose some product along the way. It doesn't disappear, it just isn't collected. So sometimes the product is lost in transfer. So when you move it from your test tube over to a flask, or if you filter it, and you're trying to scrape it off the filter paper, there may be little particles that are left behind. You'll lose some of your product that way. Sometimes some of the chemicals don't react, or they produce something different. And sometimes you have a product that's in solution and you're trying to get it to precipitate out and form a solid, but some of it stays dissolved. So these are some reasons why it might happen. Okay. So while we can get less for our actual yield, we can never get more. To get more would be conjuring atoms into existence out of nothing. Okay, it would mean that I didn't have starting materials to make this much, but magically I got more. So we'll never ever be more than the theoretical yield. That can happen where it looks like it's more than 100%. So if you're in a lab and you weigh out your material and it's more than you should have, this may have happened with your sand, salt, and ammonium chloride, where your sand weighed more than the starting materials altogether. It was probably wet. Okay, so a lot of times we're collecting things after they've been dissolved. If it's wet, you're weighing your product and water. You might also have something else that's mixed in with it from a side reaction, in which case it's your product plus a contaminant. Okay, so you shouldn't have over 100%. If you do, it's contaminated with water or something else. So we don't always start with the same amounts. And if we're trying to reproduce what somebody else did or scale it up so that we can make a product, maybe we're making a medicine to be used to cure a disease, or a new polymer that's going to be stronger and protect people's heads when they have helmets on or something like that. We want to know in any case what happens. So we're going to look at a percent yield. So that's going to be the actual yield divided by the theoretical yield times 100%. So suppose my theoretical yield is 115 grams, but I go into the lab and for whatever reason I get side products, I can't collect it all, whatever happens, my actual yield is 87 grams. Then I would say 87 over 115. The bottom is the whole amount that I should get. The top is the part that I did get. And then always multiply that by 100%. So you'll do that in lab from time to time. Now, a lot of chemical reactions involve multiple steps. reaction, you can lose some of your product along the way. Your first step, you transferred it and not all of it transferred over. The next step, you got two different products, but only one of them was useful. The next step, when you tried to precipitate it out, some of it stayed dissolved. And so each step, you have a percent yield. So to find your overall percent yield, you're going to combine the 3 or 4 or 7 or 10% yields along the way. What you do is you turn each percent back into its decimal form. You're going to take the percent divided by 100, that puts it back into decimal form. And you're going to do that for each step. So I have a subscript of 1, 2, so on and so forth for each step. And then once you got all of those multiplied by each other, then you put it back into a percent by multiplying by 100. Okay, so let's suppose we have step 1 was really lousy. We only got 36%. And then we did really great in step 2. We had 98%. And then step 3 was mediocre. We had 81%. Okay, so we'll show you in just a second, putting all of this together. But what do you think? Are we going to be able to get more than 98% out of this? No. I'm definitely less than 98. Do you think I'll end up between 98 and 81? Probably not. Think I'll end up between 81 and 36? Do you think I'll end up less than 36? All right, so let's try putting this together. Plug that in, see what you get. So you end up with right about 28 or 29%. And around to the even, 28. Once we've lost, this is the difference between this and 100% is about 64. Once we've lost that 64%, we can never get it back again. It is gone. So the best we can hope for after step 1 is 36%. So every step along the way, we're trying to keep it as close to that amount as we can, but our overall will always be less than the lowest percent yield along the way. Okay, so mentally we were probably thinking, oh, what's the average? It's not the average. It is the lowest of all these. Okay, I really quickly want to introduce oxidation numbers. We're going to go into more detail on Wednesday. This is the very last thing in section 4.2. If you wanted to take a look at it. This is a way of looking at the charge of atoms that don't really have charges. So we know ionic compounds, our atoms have charges, but if I have an atom that, or a molecule that is a covalent compound, or if I have a polyatomic ion, I don't really have charges for those individual atoms. Okay, so oxidation numbers is a way of thinking about each atom as if they've transferred electrons to one of the two atoms in the bond. So in a shared, in a bonding situation, we're sharing electrons. But if we're going to figure out the oxidation number, we're going to look at, well, what if one of them got it? Well, which one gets it is the one that is closest to fluorine. And we will talk about either in December or in January, depending on how fast things go, why that's the case. But for right now, we'll just say fluorine likes the electrons the most, and the elements that are closest to fluorine also like electrons. Okay. So two quick rules and then we'll save the rest for later. For a neutral element, that means only one kind of element is in there. The oxidation number is equal to 0. Okay, so whether I'm dealing with a metal or a noble gas where I just have one atom written, or even if I have diatomic, okay, those all oxidation number is 0. And then the second rule for a monoatomic, mono means one, ion, the oxidation number equals the charge. Okay, so those are pretty easy to remember. So that means for sodium plus, we have +1. For chloride, we have -1. All right, so we haven't really gotten to the question of what if we're in compounds. We'll deal with that on Wednesday. Any questions before you leave? All right, I will see you all on Wednesday.